in this section, we're going to consider the torsion of a structure. So take this rod, apply a twisting couple along the long axis, or a torque, and you'll see that these initially straight lines will be contorted. And so our goal in this chapter is to be able to evaluate the stress and the strain within this structure. And so the way we'll do that is we'll consider a rod that's cantilevered to the wall. And so what we have here is, imagine a plane running through this structure. That's this white line here that runs all the way back to the wall. And what we're going to do is we're going to apply a torque, or a twisting couple, about the x-axis that's going to cause that plane to rotate. And it's going to rotate by some angle, which we'll denote by phi, and that'll be the angle of twist. Now, because this rod is fixed to the wall back here, this angle will be at a maximum at the outer edge, and it will have to go all the way back linearly and meet the wall at the same spot where the initial undeformed plane was. And so phi is going to be a function of x. And this angle here that the initial plane makes with this new plane is going to be gamma, our shear strain. And so it'll be useful to look at this by making an imaginary cut through the center of this rod and trying to analyze the stress within this structure. And so here's our cross section, and here's the center of our cross section. And since we're dealing with circular cross section structures throughout this chapter, it makes sense to, instead of working in Cartesian coordinates, to work in polar coordinates. And so in polar coordinates, if you travel a distance along the cross section out to some new point, that'll be denoted by the Greek symbol phi. And if you go all the way out from the origin to the edge, that's denoted by c. That's effectively just the radius of this rod. And so when rho is equal to 0, you're at the origin. When rho is equal to the radius, you're at c. And rho is just basically the axis from the origin to the outer wall of this structure. So again, we can denote our undeformed plane. That's going to run back along the long axis of the rod. And this length of the structure here is dx. And so this is initially 90 degrees. If we apply our twisting couple that runs along the long axis of this structure, a torque about x, then what we'll find is that this undeformed structure will be twisted by some small amount d phi this new angle here, which used to be 90, is now denoted by, we could think of that as theta prime. And if we recall our initial definition of a shear strain, it was that gamma is equal to pi over 2, or 90 degrees, minus theta prime. And so this angle in here, gamma, is accounting for the shear strain within this structure. So what we're interested in here, based on this triangle, is just the ratio of d phi to dx. Except, as you'll note, as you go from the origin to the outer edge of the surface, the arc length, d theta, is going to vary. And so what we need to have here is that gamma is equal to phi, so where you are along the cross section, times d phi dx. Another thing you'll note is that as this thing increases linearly from the origin to the edge, this shear strain is going to be 0 at the center. So when phi equals 0, our shear strain is 0. And our shear strain is going to be a max at when phi is equal to the radius. Or you could write this a different way, that the shear strain is equal to phi over c times gamma max. So in this case here it says exactly what we just said. When phi is equal to 0, our shear strain is equal to 0. And when phi is equal to c, which means you're at the outer edge, our shear strain is at a maximum. It's equal to the maximum shear strain. From Hooke's law, we know that our stress is linearly proportional to our strain, which means that if we know that our strain goes from 0 to a maximum at the outer edge, we know that our stress has to do the exact same thing. So our stress will be at a maximum stress. So we can look at our stress by evaluating an area at some point phi. And it's going to follow the same form. Our stress will be at a maximum when phi is equal to c, and it'll be 0 when phi is equal to 0. So, in this case, what we want to be able to know is how do we actually evaluate the stress within this structure. And so I've already drawn on this cross-section an area element, dA. And so we can write that there's going to be a small amount of force, dF, which is equal to our shear stress times that area. Now, we know that our twisting couple has a force and a moment arm, and so if this is our force, our arm is just going to be the distance we are away from the origin. So we could write that some incremental torque is going to be equal to rho times tau dA, where here's our force and here's our arm, or our length. And so now we have our differential elements here, and so we can simply integrate this and say that our torque is going to be equal to the integral over the area of rho times tau dA. And so what we know is we can replace what we have here into this integral, such that we integrate over the area of rho times rho over c times tau max dA. So in this case now, we're going to have a squared rho, and we're going to end up with tau max over c. Tau max over c is a constant, so we can rewrite this integral such that we can pull out tau max over the radius. The maximum stress is going to be a constant, the radius of the cylinder is going to be a constant, and we're left with the integral over the area of rho squared dA. Now hopefully this looks familiar. This term here, this integral of rho squared dA, is the second moment of area. It's actually the polar second moment of area, since we're in polar coordinates. And this is often denoted by the symbol capital J. And you might recall that some simple forms for J, especially since we're going to be dealing with circular cross-sections, are that J for a solid circular cross-section is going to be pi over 2 times c to the 4th. Another common second polar moment of inertia that we're going to encounter in this course is when we have a hollow cylinder. And so, just like calculating your area, you're going to end up with pi over 2 times the outer radius to the fourth minus the inner radius to the fourth. And if you're interested in seeing where these come from, recall this can be found in the appendix of your textbook. Okay, so now we're starting to get somewhere. Now we can write that our torque is just simply our tau max over c times j. And now it would be more useful to, instead of writing this in terms of the torque, to write this in terms of the shear stress, such that our maximum shear stress is equal to the torque times our radius over j. So if this is our maximum shear stress, because we're at the outer edge of the cylinder, our shear stress at any point along rho, so just tau at any point along rho, is simply tau is equal to T times rho over j. It's important to note that all of these things can actually vary along the x-axis, and so you might find it useful to remember that tau can be a function of x, our torque can be a function of x, and our second polar moment of area, j, can be a function of x. So now we have a description of the shear stress in terms of the torque, where you are along the cross-sectional area, and the second polar moment of area of the structure. So we can go back to our initial definition for our strain and be able to say something about our shear strain in relation to our torque. And so what you'll remember is we can rewrite this instead of in the form of in terms of gamma, we can write it in terms of our angle of twist. And so if we do that, we would see that d phi is equal to gamma over rho times dx. Now we know that gamma from Hooke's law is equal to our shear stress over g. And so we can simply replace this with tau rho g dx. And we can use our formula for tau such that d phi is equal to t over j g dx. Notice we've canceled out the rho's from the definition of tau and our angle of twist. And so now if we're interested in our angle of twist, so as you apply a torque, how much is this bar going to twist? We can simply integrate this. And so our angle of twist as a function of x will be equal to the integral along the length of this structure, so from 0 to L, of our torque, which could be a function of x, recall, j, which could be a function of x, and g, which could be a function of x, all times dx. So this is the general form for our angle of twist, although you'll often encounter it in a much simpler case, in which way we can assume that our torque, our shear modulus, and our second polar moment of inertia are all constant along the x-axis, and therefore if you integrate this along the length, you find that our angle of twist will just be t times L over j g. And just like we did when we dealt with the displacements, because all of this is linear, we can consider our total angle of twist to be a superposition, so we can sum over all the different torques, lengths, second polar moments of area, and G. And so now we've described our shear strain, our shear stress, and our angle of twist as we apply a torque or a twisting couple to a rod with a circular cross section.